Welcome everyone. I'm Ralph Clayton, host of the VTM podcast. This is episode 20. Today, I want to take you into one of the quiet revolutions taking place at the edge of materials science and civil engineering, self-healing materials, smart infrastructure, coatings that repair themselves, sensors buried inside bridges, tunnels, roads, pipes, and buildings, concrete that seals its own cracks, asphalt that may one day close, wounds before they become potholes, and structures that can detect micro-damage before the human eye ever sees danger. This is not simply a story about stronger materials. It is not simply a story about better bridges or longer, lasting roads. And it is not only a story about technology trying to save money on maintenance. At its deepest level, this episode asks one dangerous question. What if the built world could learn to feel its own wounds? Because modern civilization is held together by materials most people never think about. Concrete, steel, asphalt, polymers, cables, pipes, reinforcement bars, adhesives, sealants, composites, the quiet matter beneath daily life. We walk on it, drive over it, sleep inside it, send water through it, carry power through it, trust our children to schools built from it, trust our bodies to hospitals supported by it, trust our economies to ports, tunnels, bridges, roads, rails, dams, towers, and pipelines made from it. And most of the time, we do not notice it. That is the strange fate of infrastructure. When it works, it disappears. A bridge is not praised every morning for not falling. A pipe is not thanked every day for not leaking. A coating is not celebrated because corrosion has not yet begun. A road is not admired because the crack has not yet become a pothole. Infrastructure becomes visible when it fails, when the bridge closes, when the tunnel floods, when the road breaks, when the water main bursts, when rust eats through the hidden metal, when concrete spalls, when a small fracture becomes an emergency. That is the old logic of the built world. Use, inspect, repair, replace, and often discover too late that damage began long before anyone saw it. Self-healing materials and smart infrastructure are attempts to change that logic. They ask whether materials can do more than passively endure, whether a coating can respond when it is scratched, whether concrete can seal a crack before water and chloride reach the steel inside, whether asphalt can repair microcracks before traffic and whether turn them into potholes, whether sensors can listen to the strain, vibration, corrosion, and fatigue of a structure, whether a bridge can become not only a thing inspected every few years, but a living stream of information. This does not mean bridges will become alive. It does not mean roads will think. It does not mean buildings will heal like skin, but it does mean the boundary between material and machine is beginning to change. The future structure may not be silent. It may report. It may warn. It may resist damage. It may slow decay. It may carry a digital twin. It may contain fibers that sense strain. It may contain capsules that rupture when cracks form. It may contain bacteria that sleep for years and wake only when water enters a fracture. It may contain corrosion inhibitors that remain hidden until damage exposes metal to attack. That is the new vision, not immortal infrastructure. There is no such thing, but infrastructure with memory, infrastructure with warning, infrastructure with repair built into its material body. To understand why this matters, we have to begin with a small crack. A crack is not always a disaster. In concrete, cracking is almost inevitable. Concrete is strong in compression. It is weak in tension. It shrinks. It dries. It heats and cools. It carries loads. It moves under traffic, wind, temperature, and time. Tiny cracks form. Many are harmless at first. But a crack is also an invitation. Water enters. Chlorides enter. Oxygen enters. Freeze, thou cycles widen the wound. Steel reinforcement corrodes. Corrosion products expand. Concrete cover breaks apart. The crack becomes a path. The path becomes a disease. The disease becomes repair cost. The repair cost becomes closure, disruption, and risk. This is the first great lesson of smart materials. The most important damage is often small at the beginning. Micro damage is not dramatic. It is not cinematic. It is not the collapse. It is the whisper before the collapse, the tiny fracture, the broken coating, the first corrosion cell, the first fiber break, the first delamination, the first fatigue crack, the first strain anomaly. Traditional infrastructure management often finds damage after it has become large enough to see, measure, or require intervention. Smart infrastructure asks whether we can find the beginning earlier. Self-healing materials ask whether the material can respond before the beginning becomes a crisis. These are two different powers. One is detection. The other is repair. Together, they form a new philosophy of maintenance. Do not wait for visible failure. Do not treat the structure as mute. Do not assume the material is passive. Give the structure a nervous system. Give the material a wound response. That phrase matters, a wound response, because self-healing materials are inspired, in part, by biology. Human skin does not wait for an engineer. When cut, it begins a cascade. Blood clots. Immune cells arrive. Signals are released. Cells migrate. Tissue closes. Scar forms. The repair is not perfect, but it is automatic. Trees seal wounds. Bones remodel. Blood vessels adapt. Living systems survive because they do not merely resist damage. They respond to damage. Engineering materials traditionally do not. Steel corrodes, concrete cracks, asphalt ages, coatings scratch, polymers fracture, composites delaminate. And unless someone intervenes, the damage remains or grows. Self. Healing materials try to place some version of biological response inside non-living matter. But this must be said carefully. A self-healing coating is not skin. A self-healing concrete beam is not bone. A smart bridge is not a nervous creature. These materials do not feel pain. They do not intend repair. They follow chemistry, physics, mechanics, and design. The intelligence is not consciousness. It is engineered response. Still, the analogy is powerful because it changes the goal. Instead of asking only how to make a material stronger, we ask how to make it more resilient. A brittle material resists until it breaks. A resilient material adapts, absorbs, repairs, and continues. That difference may define the next era of infrastructure. There are two broad families of self-healing materials: extrinsic systems and intrinsic systems. Extrinsic systems contain healing agents added into the material: microcapsules, hollow fibers, vascular networks, reservoirs, nanocontainers. When damage occurs, the containers break or open. A healing agent is released. It reacts, flows, seals, polymerizes, crystallizes, inhibits corrosion, or fills the crack. This is the simplest image of self-healing. A tiny capsule hidden in the material. A crack cuts through it. The capsule ruptures. The medicine spills into the wound. Intrinsic systems are different. They do not depend on a separate stored healing agent. Instead, the material itself contains reversible chemistry or physical interactions. Dynamic bonds, hydrogen bonding, metal-ligand coordination, disulfide exchange, ionic interactions, supramolecular networks, reversible covalent bonds, polymer chains that can reconnect when given time, pressure, heat, light, moisture, or other stimulus. In an intrinsic system, the material has repair built into its own molecular architecture. Both approaches are powerful. Both have limits. Extrinsic systems can deliver strong healing agents exactly where damage occurs. But once the capsule is used, that local reservoir may be gone. Repeated healing can be difficult. Capsules may weaken the host material. They must survive mixing, curing, construction, heat, stress, and time. They must break when damage happens, but not during manufacturing. That is not simple. Intrinsic systems can, in principle, heal repeatedly. But they may need conditions that real infrastructure does not easily provide: heat, light, pressure, time, moisture, mobility of polymer chains. They may be excellent for soft materials, coatings, flexible electronics, adhesives, or sealants, but harder to use in massive concrete and steel systems. This is the second lesson. Self-healing is not one technology. It is a design strategy. And the right strategy depends on the material, the damage, the environment, the timescale, and the consequences of failure. A smartphone coating, a bridge deck, an aircraft component, a pipeline, a concrete tunnel, and an asphalt road do not have the same needs. One may need scratch repair. Another needs corrosion protection. Another needs crack sealing. Another needs fatigue monitoring. Another needs water resistance. Another needs load, bearing restoration. The phrase, self-healing, can hide enormous differences. A material may heal cosmetically. It may heal electrically. It may heal mechanically. It may heal by sealing against water. It may heal by preventing corrosion. It may recover stiffness. It may recover strength. It may only slow further damage. These are not the same. A scratch disappearing from a coating is useful, but it is not the same as a load, bearing crack, regaining full structural strength. A concrete crack sealed against water is valuable, but that does not always mean the original mechanical capacity is fully restored. An asphalt microcrack closed by heating is promising, but it does not mean a destroyed pavement can rebuild itself. So the serious question is always, what kind of healing? How much recovery? How fast? Under what conditions? How many times? At what cost? And with what proof? This is where self-healing concrete becomes one of the most important examples. Concrete is everywhere. It is the skeleton of modern civilization. Bridges, tunnels, dams, ports, pavements, water systems, sewers, wind turbine bases, nuclear facilities, sea walls. Concrete is durable, but not invulnerable. Cracks are a central weakness. So researchers have been exploring ways to make concrete seal its own cracks. Some concrete already has limited natural healing. Small cracks can sometimes close through continued hydration of unreacted cement particles or through calcium carbonate formation when water and carbon dioxide interact with calci when water and dioxium compounds. This is called autogenous healing, but it is limited. It works best in small cracks. It depends on moisture. It is not enough for many real structures. Engineered self-healing concrete tries to improve that response. One approach uses bacteria. Certain bacteria can survive in dormant spore form inside the harsh alkaline environment of concrete. When a crack forms and water enters, the spores can wake. Given nutrients, they can trigger mineral precipitation, often calcium carbonate. That mineral can fill or seal the crack. The idea sounds almost like science fiction. A bridge containing sleeping microbes. A crack opens. Water enters. The organisms wake. Stone forms in the wound. But the challenge is not only the biology. It is the engineering. The bacteria must survive mixing. They must survive cement chemistry. They must remain viable for years. Their nutrients must be protected. The system must work inside real concrete, not only in a laboratory sample. It must not weaken the material. It must be affordable. It must be safe. It must perform under freeze, those cycles, traffic, salt, drying, wetting, and decades of aging. That is the hard path from elegant experiment to infrastructure. Another approach uses capsules containing mineral agents, polymers, adhesives, or chemical reactants. When cracks form, the capsules rupture and release their contents. Another uses expansive minerals or crystalline admixtures that react with water to form products that block pores and cracks. Another uses superabsorbent polymers that swell when water enters, blocking pathways and supporting further healing. Another uses fibers to control crack width so that healing has a better chance. That last point is crucial. Self-healing often depends on crack size. A tiny crack may seal. A wide crack may not. Therefore, a successful self-healing concrete design may need both healing chemistry and crack control. The material must not only heal, it must crack in a way that healing can handle. That is an important shift. The future may not be concrete that never cracks. It may be concrete that cracks intelligently. Small, distributed, manageable, healable. Then there is asphalt. Roads fail differently from buildings. Asphalt is viscoelastic. It ages. It oxidizes. It stiffens. It cracks under traffic and weather. Water enters. Freeze. Those cycles expand damage. Loads turn cracks into potholes. Potholes are not just inconveniences. They damage vehicles, slow traffic, increase maintenance costs, create safety hazards, and represent the visible end of invisible material fatigue. Asphalt has some natural healing ability. Given time and the right temperature, bitumen can flow and close small cracks. But in real roads, traffic, aging, temperature, and weather often overwhelm that ability. So researchers have explored ways to enhance asphalt healing. Induction heating, microwave heating, steel fibers, rejuvenator capsules, hollow fibers, encapsulated oils, photorepair ideas. The basic idea behind induction or microwave healing is to heat the asphalt locally so that bitumen softens and flows back into cracks. If conductive fibers or particles are included in the asphalt, they can help generate heat under electromagnetic stimulation. The road is not healing by magic. It is being stimulated to close microcracks before they become larger failures. Other systems use capsules filled with rejuvenating agents. When cracks rupture the capsules, the rejuvenator flows into aged bitumen, softening and restoring some of its binding ability. Again, The concept is powerful, but the limits matter. How many capsules survive mixing? How many remain available years later? Does the healing agent migrate properly? Does it affect pavement strength? Does it work in winter? Does it work under real traffic? Can road agencies afford it? Can it be standardized? Can it be repaired normally when it eventually fails? This is why self-healing roads have remained both exciting and difficult. Roads are brutal laboratories. They face trucks, heat, cold water, salt sunlight, poor subgrades, drainage failures, and construction variability. A material that works in a lab cylinder must survive the world. That sentence applies to the whole field. A self-healing material must survive the world. Now consider coatings. Coatings are one of the most practical frontiers of self-healing technology, because a coating is often the first defense against corrosion. On steel bridges, pipelines, ships, offshore platforms, reinforcement systems, industrial equipment, aircraft, vehicles, energy infrastructure. The coating's job is simple to describe and difficult to maintain. Keep the environment away from vulnerable material. But coatings get scratched, abraded, cracked, weathered, exposed to salt, moisture, ultraviolet light, chemicals, and mechanical damage. Once a coating is breached, corrosion can begin beneath the surface. That makes self-healing coatings extremely attractive. A smart anti-corrosion coating may contain microcapsules or nanocontainers loaded with corrosion inhibitors, monomers, catalysts, or water repellent agents. When damage occurs, the capsule ruptures or the local chemistry triggers release. The inhibitor migrates to the exposed metal. A protective layer forms. Corrosion slows. The wound is sealed or passivated. Some containers are designed to respond not only to mechanical rupture, but to changes in pH, chloride concentration, electrochemical potential, or moisture. This is where coatings become genuinely smart. They are not simply barriers. They become responsive systems. They detect the chemical signature of danger and release protection where it is needed. That is a major shift. Traditional coatings are passive shields. Smart coatings are conditional defenses. They do not release everything at once. They wait. They respond locally. They use the damage environment as the trigger. This may be especially important for sustainable infrastructure. Corrosion is one of the great hidden destroyers of the built world. It consumes steel, weakens reinforcement, shortens service life, and forces costly repair or replacement. If coatings can extend service life, they do not only save money, they reduce material consumption. They reduce emissions associated with replacement. They reduce closures and disruptions. They make existing infrastructure last longer. And in a world already struggling to build enough. Maintaining what exists may be as important as building new. But self-healing materials alone are not enough. A structure must also be monitored. This is where smart infrastructure enters. Structural health monitoring, often called SGM, is the use of sensors and data systems to understand how a structure is behaving. Strain sensors, fiber optic sensors, accelerometers, acoustic emission sensors, corrosion sensors, moisture sensors, temperature sensors, tilt meters, displacement sensors, piezoelectric transducers, electrical resistance measurements, distributed fiber optic sensing, drones, computer vision, robotics, digital twins, machine learning. Together, these tools aim to make infrastructure less blind. A bridge may carry fiber optic sensors embedded in concrete or attached to reinforcement. Those fibers can measure strain along long distances with high spatial resolution. A tunnel may include deformation sensors. A pipeline may use acoustic or ultrasonic systems to detect cracks, leaks, or wall loss. A bridge cable may be monitored for vibration and wire breaks. A concrete structure may contain corrosion probes near reinforcement. A road may be scanned by vehicles or drones. A building may be monitored for seismic response. The goal is not merely to collect data. Data alone is not wisdom. The goal is to understand condition, damage, risk, remaining life, trend, anomaly, urgency, because the old inspection model is episodic. Someone comes, looks, measures, reports. That remains necessary. Human inspection is not going away, but sensors can add continuity. They can catch change between inspections. They can identify where inspectors should look more closely. They can support risk-based maintenance. They can reduce uncertainty. They can turn structures into measured systems. This is the third great lesson. Smart infrastructure is not about replacing engineers. It is about giving engineers better sensors. A sensor does not decide the moral weight of a bridge closure. A fiber optic cable does not understand public safety. An algorithm does not carry legal responsibility. But these tools can reveal patterns that human eyes cannot easily see. They can detect strain concentrations. They can track crack development. They can notice vibration changes. They can recognize corrosion risk. They can identify anomalies under load. And when combined with models, they can help forecast deterioration. This is where digital twins become important. A digital twin is not simply a 3D model. At its best, it is a living computational representation of a real asset. A bridge, tunnel, building, pipe network, rail line or power facility. It receives data. It updates condition. It compares expected behavior with observed behavior. It can support maintenance decisions. It can test scenarios. It can help answer. What happens if the load increases? What happens if corrosion continues? What happens if a crack grows? What happens after a storm, earthquake, overload or impact? What should be inspected first? Which repair matters most? This is powerful. But again, there is danger in language. A digital twin is only as good as its data, model, assumptions, calibration, and governance. A bad twin is not insight. It is false confidence. Sensors drift. Data streams fail. Models simplify. Algorithms learn from incomplete histories. Structures contain hidden details. Construction records may be wrong. Damage may happen where sensors are not placed. A bridge does not become safe because someone built a dashboard. A smart system must be maintained as seriously as the physical structure. Otherwise, smart infrastructure becomes decorative technology. The same is true of artificial intelligence. AI can help inspect images, classify defects, detect anomalies, fuse sensor data, predict deterioration, prioritize maintenance, analyze drone footage, listen for abnormal vibration signatures, support decision making across large infrastructure networks. But AI is not a substitute for engineering judgment. It is a tool, a powerful tool, a useful tool, a dangerous tool if treated as an oracle. Because infrastructure failures are not only technical events, they are public events. They involve human life, trust, responsibility, funding, regulation, maintenance culture. A false negative can be catastrophic. A false positive can waste resources and close essential routes unnecessarily. So AI must be explainable enough, validated enough, and integrated carefully enough to serve engineers, rather than replace accountability. The future is not a bridge that knows. It is safe. The future is a bridge whose behavior is better measured, better modeled, and better understood. There is another category that sits between material and sensor. Self-sensing materials. These are materials that can act as part of the sensing system themselves. Concrete, for example, can be modified with conductive fillers such as carbon nanotubes, graphene, nanoplatelets, carbon fibers, or other materials. As the concrete is strained, cracked, or damaged, its electrical properties may change. That change can be measured. The material becomes its own sensor. This idea is extraordinary. Instead of placing sensors only at selected points, the structure's material may report distributed damage or deformation. The wall, the slab, the beam, the pavement, not silent mass. Sensing mass, again, this is not simple. Conductive fillers must be dispersed properly. They may affect workability, cost, strength, durability, and consistency. Signals must be interpreted correctly. Moisture and temperature can interfere. Large structures are messy. but the idea points toward a deeper future. Materials that carry load and information at the same time. Materials that do not only exist in space, but communicate state. This is the real transformation. The built environment is becoming informational. The old city was stone, steel, pipe, and wire. The future city may be stone, steel pipe, wire, sensor, model, algorithm, and responsive material. That brings promise. It also brings responsibility, because smart infrastructure creates data. Data about movement, traffic, stress, water use, energy systems, structural vulnerability, maintenance needs, security, critical assets. Who owns that data? Who protects it? Who interprets it? Who is liable if warnings are missed? Who decides when an algorithm's concern becomes a road closure? Who pays for upgrades? Who maintains sensors after the ribbon? Cutting ceremony is over. This is one of the most overlooked challenges. Infrastructure is long-lived. Software is short-lived. A bridge may stand for 75 years. A sensor platform may be outdated in 7. A data format may become obsolete. A company may disappear. A battery may fail. A cloud service may change. A cyber vulnerability may emerge. If smart infrastructure is to become real infrastructure, it must be maintainable across decades. Not only impressive at installation, durable in governance, durable in hardware, durable in software, durable in institutions. That is not glamorous, but it is essential. The same is true of self-healing materials. A laboratory demonstration is not the same as a 50-year service life. A self-healing system must survive manufacturing, transportation, construction, curing, temperature cycles, moisture cycles, mechanical stress, aging, chemical exposure, maintenance operations, repair compatibility, and the ordinary brutality of use. The question is not, can it heal once under ideal conditions? The question is, can it heal enough in the real environment at the right time, without creating new weaknesses, and at a cost that owners will pay? That is the path from invention to adoption. Infrastructure is conservative for a reason. When a phone coating fails, the result is annoyance. When a bridge material fails, the result can be tragedy. So new materials must prove themselves. Standards must develop. Testing must mature. Field trials must accumulate. Engineers must understand failure modes. Owners must understand life cycle value. Regulators must trust the evidence. Contractors must know how to install them. Maintenance crews must know how to inspect and repair them. The material must enter not only the lab, but the whole ecosystem of construction. That is difficult, but the pressure to do it is growing. Climate change is making infrastructure stress harsher. Heat waves, flooding, freeze, the volatility, wildfires, saltwater intrusion. Stronger storms, heavier rainfall, soil movement, higher loads, aging assets, deferred maintenance, urban growth, supply chain constraints, labor shortages. More demand on systems built for a different era. We cannot simply rebuild everything every time it cracks. We cannot inspect everything continuously by hand. We cannot afford to discover all failures late. The future requires materials that last longer, warn earlier, and repair more intelligently. This is why the field matters. Not because it makes infrastructure magical, because it makes infrastructure more resilient. Imagine a bridge deck where tiny cracks seal before chlorides reach the rebar. Imagine a steel girder whose coating releases corrosion inhibitors exactly where a scratch appears. Imagine a road surface whose microcracks are periodically healed by controlled heating before potholes form. Imagine a tunnel lining with embedded fiber optic sensors that track deformation across its full length. Imagine a water pipeline that detects acoustic signatures of small leaks before a rupture. Imagine concrete that can sense strain through changes in electrical resistance. Imagine a digital twin that helps engineers prioritize repairs across thousands of structures, not by political pressure or emergency response, but by measured condition and risk. Imagine maintenance shifting from reactive repair to anticipatory care. That is the promise. Not no failure, less surprise. Not no repair, better timed repair. Not no inspection, smarter inspection. Not immortal materials, longer lived systems. And perhaps that is the right ambition, because the built world does not need fantasy. It needs endurance. It needs structures that can age with dignity. It needs materials that fail slowly, visibly, measurably, and repairably. It needs sensors that reveal danger before collapse. It needs coatings that buy time. It needs concrete that seals small wounds. It needs roads that resist the first step toward potholes. It needs engineers equipped with data rather than only periodic snapshots. It needs public agencies able to act before crisis. This is the fourth lesson. The future of infrastructure will not be only about building. It will be about listening. Listening to strain. Listening to vibration. Listening to corrosion. Listening to moisture. Listening to heat. Listening to cracks. Listening to the small signals that precede expensive failure. And perhaps the deepest change is cultural. For a long time, infrastructure has been treated as background. Build it, forget it, complain when it breaks. That culture is no longer enough. A smart civilization cannot be careless with the systems that hold it together. Self-healing materials and smart infrastructure remind us that maintenance is not a lesser form of building. Maintenance is civilization continuing to choose not to collapse. Repair is not failure. Repair is stewardship. Inspection is not bureaucracy. Inspection is memory. Sensors are not gadgets. At their best, they are instruments of care. And materials that heal microdamage are not miracles. They are acknowledgments that damage is inevitable. But neglect does not have to be. So what are self-healing materials and smart infrastructure truly about? They are about coatings. But coatings are only the surface. They are about concrete. But concrete is only the skeleton. They are about sensors. But sensors are only the nerves. They are about microcapsules, bacteria, polymers, fibers, corrosion inhibitors, asphalt rejuvenators, conductive fillers, and digital twins. But even those are only the tools. At the deepest level, they are about changing our relationship with the built world. From passive to responsive, from reactive to anticipatory, from hidden decay to measured condition, from replacement after failure to repair before crisis, from mute structures to structures that speak. The future bridge may still be concrete and steel. The future road may still be asphalt and aggregate. The future pipe may still carry water beneath the street. But inside them, around them, and above them, another layer will grow, a layer of sensing, a layer of response, a layer of data, a layer of chemistry waiting for damage, a layer of stewardship. And if we build that layer well, the reward will not always be visible. That is the strange beauty of this field. Its success may look like nothing happened. The crack did not widen. The steel did not rust. The pothole did not form. The bridge did not close. The warning came early. The repair was small. The disaster never arrived. That is what good infrastructure does. It disappears into trust. I'm Ralph Clayton, host of the VTM podcast. Thank you for joining me for episode 20 and this look into self. Healing materials, smart infrastructure, coatings, sensors, and the science of repairing microdamage before it becomes failure. And remember, not every crack is a collapse. Not every silent structure is healthy. And sometimes, the strongest city is not the one that never breaks, but the one that learns to hear damage while it is still small.